question of whether we are alone in the universe is one of the most profound undercurrents of human thought. A persistent curiosity has echoed through civilizations, philosophers, and generations. It is not merely a scientific question but an existential inquiry, touching the core of our meaning, purpose, and loneliness. In the vastness of the universe, with billions of galaxies, each containing billions of stars, intuition suggests that life cannot be a unique gift of Earth. Yet, when we listen, the sky remains terrifyingly silent. This silence, a stark contrast between the high probability of extraterrestrial life's existence and the complete absence of evidence for it, is encapsulated in a simple yet profound question posed by physicist Enrico Fermi. Where are they? The Fermi Paradox is not an abstract puzzle. It is an empirical challenge, a shadow haunting all our efforts to find others in the universe. For decades, the effort to quantify an answer to this question has been shaped by an elegant but speculative tool, the Drake equation. Developed by astronomer Frank Drake in 1961, this equation was not intended to yield a precise number, but to structure a scientific dialogue by breaking down a grand question into a series of more manageable factors. It starts with the rate of star formation in our galaxy, then filters through probabilities, the fraction of stars with planets, the number of planets per star system that could support life, the fraction of planets that actually develop life, the fraction of life that evolves intelligence, the fraction of intelligent civilizations that develop detectable technology, and finally, multiplied by the most critical and elusive variable, the average lifespan of such a civilization. This equation, considered the second most famous in science, has served as a roadmap for astrobiology, guiding our questions and identifying the areas where our ignorance is greatest. The inherent weakness of the equation lies in its reliance on average values for the variables, which remain largely speculative, making the final result extremely sensitive to initial assumptions. However, the scientific landscape has changed dramatically since the first SETI meeting. The search for extraterrestrial intelligence, where this equation was introduced. We no longer just speculate about exoplanets, we have cataloged thousands. This shift from speculation to statistics has paved the way for a new, more robust approach: large-scale computational simulations. Instead of relying on single averages, modern researchers can generate simulated galaxies, seeding them with billions of stars whose properties are sampled from actual astronomical observations. They can create planetary systems around these stars based on statistical models from our rich exoplanet data, and then model the evolution of life as a stochastic process, allowing for the inherent randomness and uncertainty of biology. By running these simulations thousands of times, science can move beyond a single number for the number of civilizations in our galaxy, with which we could communicate and generate a probability map of where civilizations might exist, how close they are likely to be to each other, and how long they must last to coexist. It is in this context of advanced methodology that a hypothetical conclusion presented in a scenario at the joint meeting of the European Planetary Science Congress and the Planetary Science Division of the American Astronomical Society in Helsinki in 2025 carries significant weight. These organizations are pillars of the global planetary science community, and such a joint meeting is indeed planned for Helsinki in September 2025. Creating a credible backdrop for an important announcement, a team of scientists from the Space Research Institute of the Austrian Academy of Sciences presented a startling result from such a galactic simulation. Their conclusion: the nearest technological civilization could be an unimaginable 33,000 light-years away from us. And for two such civilizations to coexist in the Milky Way, they must have an average lifespan of at least 280,000 years. This number is not just a distance, it is an abyss of time and space. Our Milky Way galaxy has a diameter of about 100,000 light-years, and our solar system is located about halfway from the galactic center. A distance of 33,000 light-years means a simple two-way conversation, traveling at the universe's maximum speed, would take 66,000 years. A period longer than the entire recorded history of human civilization. This conclusion, if true, would be a profound answer to the Fermi Paradox. It suggests that civilizations are not only rare but tragically isolated by insurmountable spans of space and time. It implies that the universe is not a bustling metropolis but a vast archipelago of solitary islands of consciousness. So far apart that the light from one island may never reach the shore of another. This forces us to confront a frightening possibility. The reason we don't see anyone is because the conditions for creating a sustainable technological civilization are extremely stringent. A series of great filters that almost all life in the galaxy fails to pass. The Helsinki analysis implies that these filters are a continuous sequence, a cosmic obstacle race that a planet must complete perfectly over billions of years. The first and perhaps most fundamental barrier is a geophysical issue, the presence of plate tectonics. On Earth, the constant movement of continental plates is the planet's engine, a system that supports global life. Its importance for long-term life cannot be overstated. Plate tectonics drives the carbon-silicate cycle, a thermodynamic feedback mechanism that has kept Earth's climate stable for billions of years. Volcanic activity, concentrated at plate boundaries, releases carbon dioxide into the atmosphere to warm the planet. Higher temperatures accelerate silicate rock weathering, the chemical process that removes carbon dioxide from the atmosphere and stores it in carbonate minerals. These minerals are eventually transported to the ocean floor and, through subduction, are recycled back into Earth's mantle, completing the cycle. This subtle self-regulating mechanism has acted as a thermostat for the planet, preventing Earth from falling into a permanent freeze or runaway greenhouse effect. Plate tectonics maintains a second critical filter, the Goldilocks window of carbon dioxide concentration. The existence of liquid water on a planet's surface for billions of years depends on maintaining stable temperatures regulated by the greenhouse effect. Too little carbon dioxide, the planet freezes. Too much, it becomes a furnace like Venus. Even if a planet maintains a stable climate, the evolution of a technological civilization faces another atmospheric chemical barrier, oxygen. Technological development as we know it is inseparable from the control of fire. Metallurgy, energy production, and countless industrial processes depend on combustion, and combustion requires an atmospheric oxygen threshold. Empirical evidence shows that although some materials can ignite at oxygen levels as low as 16%, self-sustaining combustion necessary to spread fire and drive a technological era requires oxygen concentrations of at least 18%. Below this threshold, fire cannot exist. Earth's own history shows this is a formidable filter. For the first 2 billion years of its existence, Earth's atmosphere was nearly devoid of oxygen. The Great Oxidation event around 2.3 billion years ago, due to the evolution of photosynthetic cyanobacteria, only raised oxygen levels to a fraction of today's. For over 1 billion years afterward, oxygen concentrations remained below 1% of current levels, too low to support complex animal life let alone fire. Only after significant oxygen surges later, starting around 800 million years ago, did the atmosphere become oxygen-rich enough to drive the Cambrian explosion and eventually allow an intelligent primate to discover fire. A planet could host microbial life for billions of years without ever accumulating enough atmospheric oxygen for a civilization to forge its first piece of metal. Yet, even if a world somehow overcomes all the above barriers, it still faces the final and perhaps greatest filter, time. This is the core of the Hansen-Key conclusion and the most elusive variable in the Drake equation, the lifespan of a technological civilization. The requirement for a 280,000-year lifespan to coexist or 10 million years for a galaxy with 10 civilizations stems directly from the absolute scale of the Milky Way. Distance imposes a time requirement. For two civilizations to have any chance of detecting each other, they must exist simultaneously across vast cosmic timescales. This filter shifts from planetary science to the unpredictable realms of sociology, politics, and psychology of intelligent species. A civilization must survive not only external threats but also its own self-destructive tendencies. The history of life on Earth is a history of extinctions. The history of human civilization is riddled with conflict and crisis. The probability that a technological species could achieve a stable, sustainable state of existence for hundreds of thousands of years, let alone millions, may be nearly zero. This final filter suggests the galaxy may be a cosmic graveyard, filled with the remnants of civilizations that rose, shone for a few millennia, and then were extinguished before their light could reach anyone else. That suggests the history of civilization, and the ability to achieve a stable, sustainable state of existence for hundreds of years, is filled with the remnants of civilizations that rose, shone for a few millennia, and then were extinguished before the light of civilizations had drifted.